Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over how to compute higher order derivatives. Okay, so before we get started, let's take a look at the notation for expressing higher order derivatives, all right? We're going to be looking at two types of ways of expressing higher order derivatives. We're going to look at the Lagrange notation and the Leibniz notation, okay? So for the function y, we're going to look at the first and second and nth derivatives, all right? So let's just make a chart here to keep our work organized. We're going to look at the Lagrange notation and the Leibniz notation, okay? All right, so what if we wanted to find the first derivative? All right, so the first derivative using the Lagrange notation is y prime, and then in the Leibniz notation is dy dx. There is a 1 here and a 1 here, but for the first derivative, you don't bother putting that number there, all right? Okay, now how about the second derivative? For the second derivative, for the Lagrange notation is y double prime, and then for the Leibniz notation is d square y dx squared. Okay, hopefully you can see a pattern here as to how to generate the derivative expression using the two notations. Okay, so for the Lagrange notation, the number of primes indicates the derivative that you're taking, or the number of times you have to differentiate the original function to arrive at that desired derivative. Leibniz, you look at the power that's attached to the d, or what the dx power is raised to. That's what tells you what the derivative is. Okay, so let's go ahead and make a generalization. So what if you're looking for the n derivative? So the Lagrange notation for the nth derivative is y parenthesis n, not y to the nth power, just y parenthesis n. And for the Leibniz, it's d n y dx to the n. Okay? So this is just a real quick overview of the notation that we're going to be using to guide our problem solving process. So let's go ahead and try out some examples. All right, so for problem number 1, if y is equal to sine x, find y double prime. Okay, let's write that again, y double prime. Now, how many times are we expected to differentiate this function to find y double prime? Now, this is the Lagrange notation for derivatives. The number of primes tell you how many times you have to differentiate the original function. So since we have 2 primes here, we are going to be differentiating twice. Okay, so we have y equals sine x. When we differentiate first, y prime is going to be the derivative of cosine, derivative of sine, which is cosine x. Now let's differentiate again. The derivative of y prime is y double prime, which is equal to the derivative of cosine x, which is negative sine x. Okay, so there goes your final answer. Let's take a look at question number 2. So for question 2, we are to find the potential points of inflection, potential points of inflection for the function y equals 3x to the third plus 2x squared. Okay, so what is this problem asking us to do? What is involved in finding the potential points of inflection? So you have a point of inflection, point of inflection at a particular point x equals a if you have two conditions. Okay, condition number one, the second derivative of the function at that point is equal to 0, and the concavity changes. Okay, so y changes concavity. What does that mean? Y changing concavity means that y changes from concave up to concave down at A, or changes from concave down to concave up at A also. Okay, so one of the two conditions, as long as there's a change in concavity and the second derivative is 0, then you have a point of inflection. Okay, so we're just looking for potential points here. So finding the second derivative and setting it equal to 0 and solving for x will help us find the potential points of inflection. Okay, in order to ensure that they are in fact points of inflection, we have to do the concavity tests at that point. Okay, so let's go ahead and solve the problem. So what we're doing here basically is we want to solve the equation. We want to solve y double prime of x equals 0. That's the goal. All right, so let's go ahead and do that. We know that y equals 3x to the third plus 2x squared. The first derivative, y prime, is equal to 9x squared plus 4x. The second derivative, y prime, which helps us find the potential points of inflection, is going to be 18x plus 4. Okay, now to find the x values where you have the potential points of inflection, we set the second derivative to 0, so we're going to set 18x plus 4 to 0. And then when we solve this, we have x equals -4 over 18, which reduces to -2 over 9. Okay, so our potential point of inflection is at x equals -2 over 9. All right, so in order to determine if it's a point of inflection, we just look at what happens before and after to see if there's a change in concavity here. And if there is, then it is a point of inflection. Okay, now let's go ahead and take a look at the last problem. So for problem 3, instructions are as follows. We are to if x of t, the position function, is given by 1 over the square root of t minus 1, you have to find the acceleration function. Okay, the acceleration function. Okay, so given the position function, how do we find the acceleration function? That's the question. So you want to remember the following relationship. You need to recall that the acceleration function a of t is equal to the second derivative of the position function. Okay, and the velocity function v of t is the first derivative of your position function. All right, and this follows that the acceleration function is the first derivative of your velocity function. All right, so that goes the relationship. So given the position function, in order to find the acceleration, we will have to differentiate our position function twice. Okay, so let's go ahead and do that. X of t is equal to 1 over the square root of t minus 1. Now, I can use the quotient rule here, but is there a way where I can rewrite it so I can avoid using that rule because it's a little bit long? So how about I express this as, express x of t as t minus 1 raised to the 1/2 power. Actually negative since I'm reciprocating. All right, and then we can just apply the chain rule here using the power rule, and then we can differentiate with ease. Okay, so let's find the first derivative, x prime of t. Using the chain rule and the power rule, we will have negative 1/2 times t minus 1 raised to the negative 3 over 2. Derivative of 1 is just 1 times 1. Now let's differentiate this again to find the acceleration function. X double prime of t is going to now be, we'll multiply negative 3 over 2 to negative 1/2, so that yields 3 over 4 times t minus 1, subtract 1 from that again, negative 5 over 2, times the derivative of t minus 1 is 1. All right? Now, that's our acceleration function. So let's write it nicely. So we have a of t is 3 divided by 4 times the square root of t minus 1 to the 5th power. Okay, so this is your acceleration function using higher order derivatives. Thanks so much for taking the time to watch this presentation. Really appreciate it. Feel free to subscribe to our channel for updates to other cool tutorials such as this. And do post a comment in the comment section to let us know what you think about this clip. More clips can be found on mathgotserved.com. Thanks again for watching and have a wonderful day.